we in the medical professionals, we will call this the erythrocyte. Red cell. It's a non-nucleated cell. Non-nucleated. Okay? Another cell which does not keep its nuclei. The idea. Alright, so we have the erythrocyte, which is the RBC. If you look at it, it is one of the most beautiful cells, very interesting in nature because it is non-nucleated. If you look at it from the side, it looks like a dumbbell or with a biconcave shape. Can you see this? The peripheral part is more broad compared to the center. This is 2.2 microns in the periphery. But in the center, the thickness of the cell is only 1 micron. Okay? That is why when you look at the cell from the front, it looks like a target or put almost. This is 7.2 microns in diameter. The average width of those 7.2 microns. The periphery is a little darker than the center. So there is a central parallel you see in these cells. Okay? We understand this. Biconcave, double shape, sometimes you can use this kind of shape. The RBC is unique in that it lasts for 120 days. The lifespan is 120 days. It's saved and it is one of those cells which does not have any mitochondria. No mitochondria. Mitochondria is necessary for energy. No mitochondria means no electron chain, no Krebs cycle, meaning no PCA cycle. Do you remember? Glucose, you look at it. So get converted to pyruvate. Again, which pathway? Emden-Neurov pathway. Remember? Emden-Neurov pathway. ERP. This pyruvate, if it is aerobic destruction, it will become acetyl coenzyme A, which undergoes PCA cycle or Krebs cycle. We call this Krebs cycle. And this gives you the raw materials to make electron transport chain. But here, pyruvate in anaerobic conditions will become lactate. Okay? Lactate. Your RBCs make lactate. They do not have mitochondria, so they cannot undergo Krebs cycle and electron transport chain. It does not happen in RBCs. The other source of energy for the RBC is HMP pathway. HMP. Hexose monophosphate. Shunt pathway. Hexose monophosphates are the shunt pathway. HMP pathway. This pathway has many functions. One is it makes NADP, H. Reduced form of NADP. That is a kind of energy. This is a source of energy. Apart from ADP, which is made from the Emden-Neurov pathway, you have the hexose monophosphate shunt pathway, which takes your carbohydrates and converts them to NADP using a very important enzyme called glucose 6-phosphate dehydrogenase. Glucose 6-phosphate dehydrogenase. Very important enzyme. It's the rate limiting enzyme. That means in this series of reactions, if this enzyme is not there, nothing is going to progress. It's the most important enzyme in this pathway. HMP also converts one kind of sugar molecule into another kind of sugar molecule. Let's say you have glucose, but you don't have any 5-carbon sugar or 4-carbon molecule. So HMP converts one kind of sugar with so many carbons to another kind of sugar with different carbons, which your body needs at that time. You understand how we clear this? So the main thing is it makes an ADP along with the carbohydrate conversion thing that you learn about in biochemistry. And what's more important is the NADPH that is produced, NADPH2, it converts or it keeps the It keeps your red cells young. Your red cells, they age and they die. Yes, they are living and being exposed to different abuses from its 120-day life cycle. It builds up free radicals inside it. That is where GSH comes and takes away those free radicals. If the GSH is in the reduced state, very good. It will keep eating up these free radicals, preventing the aging of the RBC, allowing the RBC to reach the ripe old age of 120 years. If you have deficiency in glucose 6-phosphate dehydrogenase, you will not be able to make GSH. Okay? Are we clear? This is your glutamate, GSH, we call it glutamate, which is the antioxidant of the RBC, which helps in keeping lifespan going up. Some people have this deficiency. This is seen especially in the Middle Eastern communities, in the Arab communities. So these people, if they take certain drugs are there which will make a lot of free radicals inside the cells. These free radicals which are supposed to be counteracted by your NADPH and by your glutamate. So what happens is, it is going to cause destruction of the RBCs when you expose them to certain drugs. Usually antimalarials and some other antibiotics which are used for bacteria. Are you clear with this? Any doubts? So, your glutathione, GSH is called glutathione. Glutathione, that is the so-called GSH. That is the antioxidant. Now, let's continue. How do we make these RBCs? How are these RBCs? Let's see. RBCs are linked to a process called erythropoiesis. This is an important dead marker. You will find out. All red cells made. Erythropoiesis can come as an easy 5 marker or 10 marker, very commonly asked question in the exam. Where is produced? Where? Very good, one metal. That is after birth. It is produced in your bone marrow. There is in utero and postnatal after birth. In utero, when you're still in the womb, and postnatal after delivery, there are different sites. So pregnancy usually lasts for how many months? 9 months. So your pregnancy is divided roughly into 3 divisions, 3 trimesters. Very good. So the first trimester is roughly from the time of conception to the first 3 months. Second trimester is from 3 to 6 months. You don't have to keep it like that. And 6 to 9 months is the first trimester. Right? So your first trimester, the production of your RBCs, it happens through stem cells. It's only stem cells. Not all stages of life. The stem cells will be present in the first 3 months, located in 0 to 3 months, in utero, inside the mesoderm of your cell. So you learn embryogenesis, there's different layers of there. Ectoderm, mesoderm, endoderm. Which you know, different layers of different organs come from different parts of it. Okay? So the mesoderm is the middle layer. And then the mesoderm goes, there is one area called area vasculosa. Area vasculosa. It's what will develop into your blood vessels. So these stem cells which differentiate and become red cells are located in your mesoderm of your site, the area vasculosa, which is the only time in your body that your RBCs are produced intravascularly, like in the blood vessels. The only time in your life where your RBCs are produced while they are in some blood vessel structure is working. The first trimester. This is called the mesodermal stage. Mesodermal stage. Then, what happens is these factories, these stem cells and all these precursors, they will find a new site to work in. So they go up to, in the second trimester, from 3 to 6 months, to the liver and spleen. We call this the defending stage. mostly liver, but also spleen. And if you want to be more impressive, there are other organs where this erythropoiesis takes place, like your lungs, like your thyroid, like your testicles. So that's very minuscule in amount. Mostly, these factories are shifted to the liver and the spleen. But you can impress the example by saying also that some of these cells are present in the lungs and in the thyroid and even in the myocardial structure over there and in the testicles. They are present over there also. They will again keep multiplying and making blood in utero. Eventually, again, the factory has to shift in the third trimester. So beyond 6 months, we are going to, beyond 6 months, we are now going to medullary stage. Medullary stage. Bone marrow. Bone marrow. Every cavity of the bone. Every cavity of the bone is covered over here. Red bone marrow. So you have to shift from one factory site to another factory site to another factory site. This gives you the bone marrow production. Okay? This is the bone marrow production. This is why we need it. Then the time comes when delivery takes place of the child, pregnancy is over, the baby is born. Now you can see all of his bone marrow is red bone marrow. There are two types of bone marrow, red bone marrow and yellow bone marrow. Yellow bone marrow is just fat. It is fat. It doesn't do much, it's just to reduce bone energy. It's just over there in the bone. Okay? This is an average yellow bone marrow. But babies, bone marrow is red bone marrow. That is why these babies have so much hemoglobin. The hemoglobin goes up to 22 grams per deciliter when they are born. How much is the hemoglobin? 24 grams per deciliter. How much is your hemoglobin? 13. 13, maybe, if you are lucky. Most of you have anemia. 13, 14, 15 is like perfect number. The babies are born with 24 grams per deciliter of hemoglobin. This is not hemoglobin. They need this. They need this. Why? What do you think they need this? They have it because all of their marrow is red. Why did nature, why did God create a child with 24 grams per deciliter? So much of red blood cells. Because what do you feed a baby when it's born? Only, listen, you can't give him water, even if it's pure water. You know what's going to happen to him? You're going to get absorbed, dilute his sodium in his ECF, and cause hyponatremia. You dilute his salts. You can cause dangerous seizures. You can kill the baby. That is why we say rest is best. That's the slogan, rest milk. The osmolality, the electrolytes, composition will not shock and change the composition of the tissue fluids over there. Are we clear? Only breastfeeding for the first 6 months. So are they going to get much iron from breast? They will be very healthy if they will be breast. They will become taller, they will have lesser asthma, lesser chance of diabetes, they will be bonded more to their mother. They will be psychologically more normally developed when they have breast milk available. There is no substitute, nothing that can be as good as breast milk. That's what you wrote about the mother's breast. What about cow milk? Osmolality is too high. Buffalo milk, way too high. So you give something with high osmolality, it goes in the intestines. What's going to happen? When it takes the stomach, absorbs a lot of water, extends the stomach, causes bloating, and the child keeps crying, body pain all night. That's why I told you the formula feeds. You understand? There's no other thing here from the mother. If a mother gives birth to a premature child, her breast did not develop enough, right? It will be smaller. That osmolality from the premature breast for the premature baby is supposed to be. Slight deviation, but very interesting enough. Modern other people say let's have formula fat cell life and all that stuff. Whatever chemicals you want to give the child. In your case, we don't know how much they are giving. So we can try anyway. So without this is giving you to after birth. The baby is all bone marrow is left. As it grows older, bone marrow starts to get replaced with yellow bone marrow. So you see these bones, these are the long bones. They belong to my appendicular skeleton. You know there's axial skeleton and appendicular skeleton. You know that? Axial skeleton is like this part, the ribs and spine, these irregular shaped bones. And then you have these appendicular skeleton, the other things that are stuck in the appendage, these long bones over here. Classic bone structure, you see long and quadrants. This is your long bone. These long bones have shafts which are all filled with yellow bone. Where is the red bone marrow? The red bone marrow is in your axial skeleton. These bones are also called membranous bones. What do you call them? Membranous bones. They are irregularly shaped. They are not the classic shafts with epiphysis, metaphyseal vein. Once you study the anatomy, you're going to see long shafts of bones over here. And only at the edges where the bones look irregular, at these edges over here, with epiphyseal ends, you will find some red bone marrow among people. On the long bones, but the membranous bones, the ribs, the spine, the skull, these funny bones, and the pelvis, they will all have red bone marrow. The main site is here, but this is all yellow bone marrow in my long bones. Okay? Supposing I get anemia, I lost some blood, I eat good food, I get my iron, my B12, my folic acid, all the raw materials are good in my diet. I need to make more cells, more RBCs to replace that 1 liter of blood I got, for example. Now, you know what happens to this yellow bone marrow, this bone, the red bone marrow will say, I need to make more factories. Yellow bone marrow get out. I will expand, make this yellow bone marrow convert to red bone marrow when I need it. And then it will make more red cells, and when I'm back to normal, it will resume its original configuration eventually. You understand? So when required, the red bone marrow can expand its volume up to 10 times, increasing the amount of RBC production temporarily, whenever required, provided you keep taking the right nutrients. You understand this? This is a miracle of bone marrow. Bone marrow is a lot of stem cells. What are these stem cells? What is a stem cell? These are your basic terms you should know. Stem cell, usually when you think stem cell, it's all good, right? Stem cells are used to cure this, to cure that, can replace lost cells, anti-aging secret, use stem cells in the damaged joints, and the joints become young again. For the old man with arthritis, many things you can do with stem cells. Stem cells are cells that can multiply into many different kinds of cells, usually. They have the ability to multiply into any kind of cell. It's like a kid in 5th standard. He still hasn't decided whether to join commerce, humanities, or science. Lots of options in front of him. He's still fresh. His mind is open to receptive to experiences and to shape his life. Stem cells can differentiate. That's the word differentiate. They are undifferentiated stem cells. They will differentiate and take one particular stream. It can become a muscle. It can become a blood cell. On a blood cell, the stem cell can become a white cell, a red cell, a platelet, lymphocyte. So again, there are many options. Under some stream, you can go into computers, into biology, into AI, into data science. You have many options, right? Like that same thing. There are many options for the stem cell at different stages. Stem cell, under those asymmetrical division, what we call stochastic differentiation. So, what's that mean? One stem cell will multiply into two stem cells. You have a stem cell that decides to multiply, and what it will do is it will make one more stem cell. So one of the babies is going to be another stem cell, while the other one becomes some sort of differentiated cell with some shape, function, whatever it is. So it is differentiated to molecular tissue. But it is still maintaining a family, a population of cells that can still keep dividing and giving you more of this particular cell. You understand what stem cells are? They undergo division, but it's like if I divide into two differentiated cells, who's going to divide after these two apart? So I will make one child a stem cell and the other one will become a professional cell which will function in that tissue. It will differentiate to that tissue. You understand? Are you following me? Are you down to this so far? So this is your stochastic differentiation, this is your asymmetric division. We just said about asymmetric division. It is not the same. I will have two children, I will not make one of both of them individuals. I will take one as a stem cell, we can do anything we want to, and one can make two or more.